Hello, and welcome to the first Spotlight Live of Curious Stardust, a blog site where scientists share their ideas about astrophysics, nanoscience, and neuroscience. My name is Kellen Tuttle, and for this hangout, we're separating science fact from science fiction in the blockbuster film Interstellar. When the movie begins, the Earth is a catastrophic wasteland of dying farms and mile-high dust storms. And with just years before facing complete oblivion, humanity needs to find a new planetary home. It's a Hail Mary mission, and taking it on are 4 astronauts who must enter a wormhole, manage bends in time, and find an extremely distant habitable planet suited for a mass exodus. But just how much of the movie is really true to what we know about the universe, and how much of it is creative license? To answer this question, Curious Stardust sent 3 bloggers into the darkness of their neighborhood theaters. They've returned and are here today to answer your questions about which portions of the movie are scientifically plausible and which stretch the imagination even for a physicist. With us today are 3 astrophysicists from 3 parts of the world, on both coasts of the United States and across the pond in the United Kingdom. Here with me on the west coast of the US is Mandeep Gill, who's an observational cosmologist at the Kavli Institute for Particle Astrophysics and Cosmology. Mandeep's research focuses on gravity's bending of light and the mysteries of dark matter and dark energy. On the east coast, we have Eric Miller, who works at the MIT Kavli Institute for Astrophysics and Space Research, where he studies pockets of gas spread throughout the universe in a quest to understand how mass is structured. And in the UK, we have Hardip Sanghera, who supports the Planck Observatory, a satellite that just finished mapping the universe's earliest light. Hardip works for the Kavli Institute for Cosmology, Cambridge. Before we begin, let me remind you, if you have a question you'd like to ask our panelists, please send it to the Kavli Foundation by email at info@kavlifoundation.org or via Twitter using the hashtag KavliSciBlog. And I should warn you that if you haven't seen Interstellar yet, we are absolutely going to spoil the ending for you today. If you prefer to be surprised, you can also view this conversation at a later date on both the Curious Stardust blog and on YouTube. So before we jump into the movie itself, I'd like to begin by talking a bit about some of the phenomena in Interstellar. To help us out, Eric, how about giving us a simple explanation of a black hole? And to make it a little bit more challenging for you, and because it's nearly the Thanksgiving holiday here in the US, I'm hoping you'll explain it to us using only objects you might find in a kitchen.
Okay, I'd be happy to. That might be a little challenging. But a black hole is essentially just a very dense concentration of matter, or food, which you would find in the kitchen. And the key about a black hole is that it's so dense that there's a region around it outside of which light can't escape. And this is why it's called a black hole. And this radius at which light can't escape is called the event horizon. But the key to a black hole is not that it's massive, but that it's very dense. So in fact, a black hole can be made of very little mass, and so such as a green pea or something like that, or it can be what we call a supermassive black hole. Which I guess would be the turkey in the Thanksgiving roast, something like that. So we sort of see 2 kinds of black holes. We see what we call stellar mass black holes. These are things that form from massive stars. They have about 10 times the mass of the sun. That event horizon is on the order of 20, 30 kilometers, something like that. That would be the green pea. The turkey, which is in this movie, is a supermassive black hole, and that's something that's more like 1 million to 1 billion suns worth of mass, concentrated in a very small amount of space. But they have an event horizon that's about the size of our solar system, or the orbits of the planets. So another thing to take this back to the kitchen is that when matter goes into a black hole, think of it as a funnel. Think of that black hole as sitting in the middle of a funnel. So matter is traveling down the funnel into the black hole. Often it spins around. And so we also see that in the movie as well. So I think we'll talk about that a little bit more. But those are kind of the 2 sorts of black holes that we see in the universe. Of course, a black hole can actually have any mass. Those are sort of the ones we see. I don't think I'm putting many kitchen ingredients in there, sorry.
It's perfectly fine. There's a turkey, so I'm happy.
Okay.
And so the one term that you mentioned, this event horizon, so that's the point at which gravity is so strong that it's pulling in the light, I guess, with such force that it can't escape?
That's right. It's called the event horizon. That's right, because you can't see events. You don't have no knowledge of events inside of the black hole. And that's right. And that's where you see the thing that's black, and that's why we call it a black hole. It's not a very, very exciting description, but it's because light is not escaping from the event horizon.
Perfect. Thank you very much. Hardip, I'd like to move to you next. So you're not in the U.S., so I promise I'm not going to make you relate your answer to Thanksgiving, at least not this early in the conversation. But I am hoping you can tell us just a little bit about faraway planets. What do we know about planets in other solar systems, and are there likely to be habitable ones out there?
Well, actually, the first extrasolar planet was discovered. Can you hear me clearly? Because we had audio problems earlier.
We're good now. Thank you.
Okay, that's fine. Yeah, the first planet was discovered about 1992, and now we're up to about nearly 2,000 extrasolar planets that we know about. And this is thanks to the Kepler mission, the NASA mission. And if we extrapolate from that number, we can estimate that within our galaxy, there's probably anywhere between 100 billion and a trillion planets within our galaxy alone, right? And one of the things that we've learned from the observations that we have now, we thought our solar system was the typical scenario for solar systems around the galaxy, but actually what we find is that that's not the case. Most of the solar systems look nothing like ours at all. In fact, what you tend to find is all the big gas giants and the rocky planets that there are actually found clustered close to the stars. So they're actually usually far too hot, basically, for life or habitability as we would understand it. But there's actually a catalogue out there. I've actually wrote it down. It's called the Habitable Exoplanets Catalogue, and it lists there's about 21 planets out there at the moment which have the best chance for life beyond our solar system. So basically, they're in the habitable zone. That's the zone where we're going to have liquid water, where it's not frozen or evaporated, basically. And what we really want to find are planets that are not about smaller than about 1.5 times the size of the Earth. Because obviously, if we have a gas giant, we're going to have there's going to be no real surface to talk of. And if the planet's too small, it's not going to hold on to its atmosphere, basically. Yeah. So 21 planets that we know of that might be likely candidates for us to possibly one day inhabit. And the other funny, interesting stuff at the moment is now that if we get the light, either we get the light from the sun coming through the planet's atmosphere, or we can actually even try to isolate the light reflected from the planet, we can actually get an idea of what the weather conditions are on these planets. And on one of them, I think we know that it's hot and cloudy on half the planet. It's as much as we can tell at the moment. But maybe in a few years' time, we may be able to actually look for signatures of life. So maybe we'll see traces of traces of oxygen in the atmosphere. So you never know what's to come. But 21 planets possible at the moment.
Great, that's great background for our conversation. Thank you. And Mandeep, will you explain to us the general concept of a wormhole?
Wormholes. So in contrast, let me brush the popcorn off so we can talk clearly. This is, of these three things that you've just mentioned, this is the most speculative. We are very clear that there's exoplanets. We've seen them. We know there's black holes. We see very clear evidence of both the stellar masses Eric talked about and the very massive ones at the center of our galaxy and other places. Wormholes are a potential solution to they're called Einstein's equations, the current theory of gravity that we have, the best theory, the one that goes beyond Newton. And they were initially called Einstein-Rosen bridges back in the 20s. Einstein and Nathan Rosen wrote papers on them. But then John Wheeler coined this term wormholes, late 50s, and showed that they were unstable, even theoretically, that they would pinch off these necks. And then later it was Kip Thorne, who did the movie here with, I think, his student Mark Morris, and they showed that in some way you might be able to stabilize the two ends. So what are we talking about? The idea is that, as you see in the movie, if you've seen the movie, there's an area that is kind of the portal to an extra dimension. So they do this in the movie. So I'm going to use a two-dimensional analogy like they do. I'll use this piece of tissue paper. So if you lived in 2 dimensions on this plane, you would never see the third dimension if one existed, right, around you. But what they do in the movie is they show if somehow you could fold space and go through that third dimension, so you could jump right through it, then those two beings that are on the flat land could go through the portal over here and jump out over here very immediately. sort of the warp jump that we need, since the closest star that we see in the sky is 4 light years away, and so we have problems. So that's the idea. And so the last idea that I started mentioning that Kip Thorne and Morris did in the 80s, I think, is they talked about are there ways to stabilize the mouths of these wormholes to keep them still there? And they thought of some weird sort of negative energies and very things that we don't normally see, but we do now have this thing called dark energy. People may have heard of it. It was seen about 15 years ago that says that this is something that has energy density but a negative pressure and a constant energy density, which is completely different than all the stuff we know. So my point there is that there may be ways out there to possibly get wormholes. That's, of course, the science fiction buff's dream. So that's the quick picture.
Great. So I think with that little bit of background, let's jump into the movie. So let's work through the movie a little bit chronologically, but let's not worry about how the destruction of the Earth is portrayed. I think it's just too depressing. Let's instead start in space with the trip to Saturn. So in the film, it takes the astronauts 2 years to get from Earth to Saturn. How realistic is this? If we still had a space shuttle, could we point it towards Saturn and be there in a couple years?
I don't think the space shuttle would make it, because that's made for landing back in the Earth. But go ahead, Eric.
Yeah, that's right. I mean, the space shuttle doesn't have the necessary propulsion system to do that. I mean, we're talking about a mission to Mars, for example, taking 18 months or 2 years, and Saturn is quite a bit further than that. So I think with our current technology, the answer is no. But that certainly doesn't preclude some future technology, some future propulsion system, which will allow us to get there. And in the movie, also, there was a slingshot around Mars, which we often use for interplanetary missions, and this is just a way of stealing a little bit of angular momentum from a huge body and giving it to this tiny little spacecraft comparatively. And so that can accelerate it very, very quickly. So if we can get to Mars very fast, which I think is certainly plausible, we should be able to get to Saturn also. So with current technology, no, but I think it probably could happen.
I was going to say, I've read somewhere it took about 2.5 years with the fastest missions to get to Saturn. But if you actually wanted to land at Saturn, so you'd have to decelerate when you got there, you'd be talking about timescales of closer to 4 years. So they were a bit short in the film.
So it sounds like not something we could do right now, but maybe plausible in the future.
Yes.
Great. Okay, so we've got our astronauts, and they're heading towards Saturn because there's a wormhole nearby. And so we just got a really nice overview from Mandeep, thank you, about what a wormhole is. And I'm hoping that you guys can rate this on a nice Thanksgiving scale, from, say, the low end of Jell-O salad to the high end of a perfectly cooked turkey. How likely do you guys really think it is that these theoretical wormholes actually exist out there in the universe somewhere?
What was your low end of the scale?
Jell-O salad.
Well, I'd say yellow salad. Sorry to be a pessimist.
Eric and Mandeep, what do you think?
I sort of give it cranberry sauce. I give it somewhere in the middle, 50% chance. I mean, I like to be skeptical about these things, but I don't know.
I don't know, stuffing. It's not. They're not. Yeah, we've never come across any evidence for one. They would be very strange objects. It seems like, as they sort of talk about, maybe there's beings that can construct them. I do want to point out that even black holes are very strange objects. We might get to that. And people, when they were first theorized and Schwarzschild came out with the solution, people said, you can't have space like this because everything else we see in space is touchable and stuff. So how are you going to have a region of space that you can't get into? So there are strange things in gravity and in quantum mechanics, so I won't rule it out, but I doubt we'll find one there real soon, let's say.
I know very little about wormholes, but what I have read is that they are tiny, tiny objects. I mean, much, much smaller than the dimensions of an atomic nucleus. And they don't last for very long. They last for the tiniest, tiniest fraction of a second. So not only do you have to find one of these tiny objects, you've got to hold it, you've got to enlarge it, and then you've got to maintain it. So it doesn't collapse on itself. So it sounds all very, very unfeasible, unfortunately, to me. I mean, general relativity doesn't preclude wormholes, but it doesn't need them in any sense either.
Yep.
All right, so for now we'll suspend our disbelief and go with it. And we've got our astronauts, and they've gone through the wormhole, and on the other side they emerge, and there they find a dozen planets that are orbiting a black hole. So I have to stop there because in our solar system, our planets orbit a star, the sun, and that's how we think a great majority of solar systems work. Have we ever seen planets that are orbiting a black hole?
No, nobody has. Sorry.
Right.
That's an easy one then.
But it's not actually.
So I was going to say, we have seen planets around dense objects, compact objects like neutron stars. One of the very first planets discovered was around a neutron star. But as for black holes, no, we haven't.
Well, it's hard to see. I mean, I'm going to step up for the movie in this case because I had some discussion with friends. It could now. This is a supermassive black hole. As Eric pointed out, this is something like 1 million. The one that's in the center of our galaxy is about 3 million solar masses. They can get up to billions of solar masses. So ours is relatively small, SMBH, supermassive black hole. But there could be other stars that are orbiting it that the planets are orbiting around. They don't really show it that way. But we wouldn't see easily if planets were orbiting around black holes big ones, because they usually have an accretion disk that's shining in the X-ray and that's very bright. I don't think they went into this in the movie, but briefly, one of the coolest things about black holes are the orbits of objects that go close to them, because they don't stay in a plane. They actually go in three-dimensional orbits because of Einsteinian gravity, which is general relativity, the term Hardip mentioned before. So it's possible, I think.
But we can't detect planets with the current detection methods that we use around black holes, because we either detect planets by the wobble that planets induce on the star or the parent object around which it's orbiting, or we see it by the dimming of the light as the planet passes in front of the star. But in either case, we couldn't do that with a black hole. You wouldn't see the effect on the wobble from a planet on a black hole, and also black holes don't effectively emit radiation in the sense conventionally that we understand. So with the techniques that we use now, we wouldn't find them there anyway.
So they could be out there and we're just not seeing them quite yet.
Correct. But then you get into the issues of whether you could have stable orbits around a black hole, which is another thing altogether.
Here's a related question that a viewer has sent in, and they would like to know, could a black hole at the center of the solar system actually provide the light that's needed to support life?
Well, so yeah, I can answer it a little bit, I think. So Mandeep mentioned that, especially with a supermassive black hole such as this is, you get what's called an accretion disk around this. And this is getting back to the funnel that I was using to explain black holes. But this is essentially material that's being collected in the gravitational well of the black hole and spiraling into it and feeding the black hole. So the thing is that the gravitational energy that's released when this material falls into that accretion disk and then just collisions within the accretion disk heat it up. So you typically see it in X-rays. And in fact, we think that there's a supermassive black hole at the center of essentially every galaxy. And a lot of them are very bright in X-rays. They're called active galactic nuclei. We see them shining sort of steadily, but we also see these outbursts from them. Now, I don't think that a planet habitable by humans would probably survive there if it's bombarded with this amount of X-rays. For comparison, there's a supermassive black hole in the center of our galaxy. It's actually sort of anemic for a supermassive black hole with an accretion disk. It puts out in X-rays about the same amount of light that our sun does. So in that way, yeah, you do sort of have the same amount of energy, but it's in X-rays, and it's also, as I said, fairly anemic. So I think the answer is probably not. Any sort of life-providing atmosphere would probably be fried, and I don't think life could survive for very long there at all. So
yes, the energetic radiation, mostly in the X-rays, would probably sterilize the planets, unfortunately.
Yeah, I'll again go for the stars orbiting at a distant enough radius, then they could have planets around them. Stars orbiting the black hole, so it depends on how realistic you want to be, I guess.
That's true. It does depend on the distance. I mean, there's some other things in the movie that suggest that maybe this is closer than you would want to be.
That's true.
That's a great segue into the next viewer question. So once they enter this solar system, black hole system, whatever we're going to call it, on the first planet that they visit, time goes completely wonky on them. And for every hour they spend on the surface of that planet, 7 years pass back home. So we've had several viewers write in to ask for a rundown on how this works. You know, why would clocks run differently in two different parts of the universe?
So this is one of the things, this is probably the biggest thing that really hasn't been displayed before in movies, and that people were excited. One of the physicists I went with was really excited that this was shown. And this is called time dilation by gravity, by strong gravity, and versus time dilation by moving fast, which is well, there's two forms of, we'll use the term relativity. Most people have seen that, and we even have the equation E equals mc squared for special relativity. That's one equation we're allowed to use and say. So in the one that is due to gravity is because, let's see, light in a gravitational field falls downward, and yet it has to go at the same speed. So somebody seeing it from far away is seeing it travel on a longer path, right? Because it's shot out, but light also obeys gravity. That's one of the things that comes from Einsteinian gravity. And it falls down, so it's following a longer path than if it went straight across something. And that because it's traveling at the same speed, that eventually translates to time dilation. I don't know if one of you guys want to jump in there. Say more.
No, I mean, I think that was a good explanation. It's actually very hard to describe. It comes out of Einstein's equations, and as Mandeep mentioned, it really comes out of the speed of light being a constant in all of these reference frames. And so that essentially is what's controlling your time, is the speed of light and moving along these, well, they're called time-like paths, basically. And so Einstein's equation, or Einstein's theory of general relativity, really says the same thing happens when you're in a gravitational field as happens when you're moving quickly with respect to some other person. That's why it's general. He takes this theory of special relativity and generalizes it to a gravitational framework. And so yes, you can have this time dilation when you're really not exactly moving in space, but you're in a very different region in space-time compared to somebody else.
Can I just add that basically the clocks run slower the stronger the gravitational field. So in the 70s, scientists took atomic clocks up in planes, and when they brought them down, those clocks were running a little faster than the clocks on the ground. And another way that we actually use it in our day-to-day life is that our GPS satellites, because they're in the orbit above the Earth, their clocks are running slightly faster, and the software in them has to take account of that fact in order to be able to give us a proper time signal on the ground. So we use general relativity with our GPS satellites to be able to give us a proper clock signal. And it was nice to see that actually portrayed properly in the movie.
Yeah, I'd like to go to that because lots of times, we do these esoteric seeming things, and I really do think that applications that come out of these things are important to talk about because everything gets used eventually. And people thought that at some point you wouldn't ever use general relativity and that kind of gravity in any situation, but it's turned out that like Hardip said, you would be off by I think it's hundreds of meters if the GPS satellites didn't account for that. And we measured this stuff on the Earth. You can actually, I think the first experiment was called the Pound-Rebka experiment. They took it up in a tower at Harvard, and I think this was really early in the 1920s, 30s, where they just took a clock up and just sat there, and they could see that there was time dilation in the clock on the ground, closer to the center of the Earth. The clocks ran slower than farther away from the gravitational field. Pretty amazing.
So one of our viewers has a really interesting thought experiment question from this. So he says, suppose the folks on the surface of this planet, where time is traveling or time is passing differently, decided to radio their friend back on the ship to sing him happy birthday. Would the friend back on the ship have perceived them singing excruciatingly slowly?
Yeah, I mean, it's all about like how do the photons. We see this sort of gravitational redshift. You can actually see it from any star because the photons have to come out of the potential well near the star, and they get a little bit redshifted as they come towards us. So yeah, you would see weird effects, especially if they're in a very strong gravitational field. But it's I don't know that you would see them singing from that far. What do you guys think about that?
Yeah, so actually, just to comment a little more on that, the gravitational redshift, what that means is that whatever frequency they're using to send this radio broadcast, the frequency at which it leaves is going to be different when it arrives. It's going to be redshifted. So the frequency is going to be much lower when it's received on the ship. So the ship's going to have to tune to that frequency. The wavelength will be much longer. I don't know whether the signal, when it's decoded, what it will sound like. I mean, maybe it depends whether you're using FM or AM or something like that. But just to turn that around a little bit, you can imagine if they recorded a message like on a thumb drive or a cassette tape or something like that, and brought it back with them on the ship, it would sound the same, because it's all the mechanical stuff in there is working in its local time dilated framework, and when it's brought back to the ship, it will work the same way in that local framework. The radio message, I'm not exactly sure, because you have to think about how the information is actually modulated in the particular radio transmission. We have a radio astronomer here. Maybe he knows, just to put him on the spot.
I'm not sure how to answer the question myself, actually.
I think it's something we need to think about. But I guess if it's FM, if it's frequency modulated, I think you just have to tune to a different frequency. But I bet it will sound the same as long as you modulate it properly.
So we have another viewer question about the same planet, but on a whole different topic. So on this planet, it's a water world. And so if the astronauts are on that world and they're standing in deep water, and suddenly this huge wave starts to approach them. And so we've had a couple viewers write in and ask, why is there no discernible movement in the water that they're standing in? Like no water sucking back toward the wave. Is there any way that this could actually happen?
So I thought that the way they did the tides on that planet, I mean, I didn't really like it from a science standpoint. So the way that the tide works on the Earth, or essentially any body, essentially, you have this round thing, and if the moon is up here and the sun is down here, you have this bulge of water, and the Earth is rotating under that bulge. And so the tide would work in the same way on this planet. You would kind of have this bulge pointing towards the supermassive black hole, and the world would be turning under it. So in fact, if you had one of these waves every hour, that Earth or the planet would have to be spinning once every 2 hours, incredibly fast, 10 times the speed of the Earth, because it's kind of a similar gravity, probably similar density. So I think what you would see if you were just a boat or something on that water is you would just kind of go up and down quickly, but I don't think you would actually notice it, especially since there isn't any land mass. So having these very spiky, sharp waves, I think, is Hollywood. I think that's fiction.
It was certainly exciting, though.
Yeah.
All right, one more question about this Earth, this planet. A viewer has asked, if astronauts used a rocket to get off Earth, how could they possibly use a single Ranger to take off from this first planet, where I think gravity was, what, 130% of gravity on the Earth?
Yeah.
Please, go ahead.
I should say this is one of those holes in the film. I mean, yes, to go to those planets, they needed exactly the same mechanism. They would have needed a rocket booster system to get off those planets. Going down's easy enough, but getting off, to get the escape velocity, they would have needed, like on Earth, a 3-stage rocket. So it's one of those story plot lines. I mean, in Star Trek, they use transporters and things to get on and off the planet. It's one of those holes. There was quite a lot of holes in the film scientifically, but for the story, I mean, in a similar vein, there was no, on the Endurance, which is the craft they took to get to Saturn, there was no obvious fuel tanks on there. So you wondered, how did such a spaceship get from Earth to Saturn without a vast amount of fuel, both to carry you there and also to slow you down?
Yeah. Well, fuel tanks aren't photogenic. I think that's probably why.
Eric, say that one more time. I'm sorry.
Fuel tanks aren't photogenic.
That's true. But I think you guys are all a little bit spoiled sports. I really like the adventure aspect of the movie a lot, and trying to solve these problems on the Earth. So perhaps they have invented antimatter drives, which would take very little. We are looking at plasma drives now, but antimatter drives would, if you could create enough antimatter and propel it out the back, you would need very little of it. The total amount of antimatter we've ever created on the Earth is less than a microgram, I think a millionth of a gram. So it's pretty expensive stuff. Actually, the science special at the end of Angels and Demons, if you care about antimatter, is really good. Tom Hanks narrates that. That's a separate topic. But there's ways to think about it. But on the face of it, some of these things might be hard.
Great. So let's skip ahead in the film a little bit. The astronauts go and visit another planet, which truthfully isn't as scientifically interesting as the first one, and then they want to make it to a third planet, but they don't have enough fuel. So back to the same question. To overcome this, they slingshot themselves around the black hole, and then one of the astronauts, this is Cooper, ejects himself from the main spacecraft to help his colleague have enough momentum to reach that third planet. Can you guys run us through this? How do these two components help? How can you get around the problem of having no fuel by slingshotting and then ejecting? It's a big question.
It is a good question. So as I mentioned when we were talking early on about the trip to Saturn, they slingshot around Mars, and so it works if you have a spinning black hole. So the original solution to Einstein's equations that Schwarzschild came up with many years ago. He simply had a static black hole. It was a black hole was sitting there in space, had no spin, no charge, just mass. So since then, there's been Kerr came up with another version of a black hole, which is a spinning black hole. And the thing about the spin is that it actually drags space-time around with it outside of the event horizon. So in fact, there's a region outside of the event horizon that the spinning affects. And if you go into that region, you don't have to go into the event horizon. You can successfully go into that region and come back out the other side. You have to be traveling very fast to do it. You can actually steal some of the spin of the black hole in the same way that you steal some of the angular momentum of a rotating or revolving planet, and gain speed from that and change also your direction of velocity as well. The way that this works with a spinning black hole, however, is that you actually have to leave some of your mass behind, and that's how you exchange the energy, is by giving some of your rest mass energy to the black hole. And so that's what they did. They took energy from the black hole, converted it into translational into velocity, and somehow she was able to get to the planet that way.
There you go. Can I mention a sciencey aside?
Please do.
Because we're not going to be slingshotting around black holes real soon. But one of the coolest things that I think that Eric was mentioning, spinning black holes, and most things in the universe spin because they're in free space. So most black holes spin. Some of them spin very fast. And the faster they spin, the more they do this frame dragging. Actually, there was a cool experiment called Gravity Probe B that checked that around the Earth. But the neat thing about black holes is you can actually see their shadow deformed, and it looks something like a lima beam because of this spinning. It's different on one side than the other, and we think we're going to be able to see that reasonably soon. Probably within some years, we built a radio telescope, because that's what you're using to look behind it. Well, it's an array. It's the Event Horizon Telescope. It did several telescopes. There's one in Greenland and other places. So if people want to look that up, the one at the center of the black hole, which is center of the Milky Way, is pretty massive, 3 million solar masses. Then there's another one that's a few billion solar masses, but much farther away from us. And those are the two targets that we hope to see. That's going to be incredibly cool if we can get, quote, real pictures of the black hole, of that spinning part.
Very cool. So as part of this whole interaction, Cooper ends up actually propelling himself toward the black hole. So I'm hoping you guys can describe a little bit what science tells us it might be like to approach the edge of a black hole and how it compares to the film.
Well, we don't know. Lots of people have thought of a lot of things. It's going to be hot if you're coming in along the accretion disk. As Eric mentioned, you have X-rays coming out along that disk. That's the disk where everything is funneled around. It's a pancake, and it's hot. So you probably don't want to go in along the disk. Although Cooper skins her eye line because he's a brave guy in the movie. But if you come in on the pole, as long as there's no jet shooting out of energetic particles, maybe at 45 degrees, maybe it's dark enough that there's this whole thing where if it's small, you're going to be tidally stretched because tidal forces are much stronger than gravitational. Tidal forces are the things that cause tides and pull you apart.
And there's in fact a very appropriate term for that for Thanksgiving, isn't there? Spaghettification.
Spaghettification. We have a that's right. We have a nice post on the the KaiPak blog about that from a couple months ago. I think we'll have references somewhere here later, just in case people want to. It's a really cool thing. That's right. So you get spaghettified, but if it's big enough, you don't feel those tidal forces that much, and you might be able to go in. So you guys know better than I what happens when you go into a black hole, right?
That's right. From what I've read, that for small black holes, the tidal effects would be so strong you'd get pulled and torn apart. So you saw that happening with his spaceship, but not to the astronaut. But supposedly for very supermassive black holes, when we're talking about 100 million solar masses, the actual tidal effects are very gradual. So supposedly you could survive a fall into the black hole and over the event horizon. He wouldn't know that he was going over the event horizon when that happened. Only an external observer would see that actually happening for him. He would just pass through it and go straight into the black hole. Once he's into the black hole, it's anybody's guess what goes on in there.
Let's talk a little bit about that. So we're running out of time, but I want to make sure that we talk about that. So inside the black hole, Cooper enters this strange realm where he experiences time as a spatial dimension. Do we have any idea if such things might possibly exist, whether it's inside a black hole or not?
No, I mean, I think this is all speculation, and a lot of this is science fiction. I mean, certainly there's room for it. You can put a lot of things into Einstein's equations, but really, I think this is science fiction. So if you start going into higher dimensions, certainly you can do almost anything, and I think that's exactly what they did there. It was interesting when he was going to the black hole. I think what Hardip said is right. When you're crossing the event horizon, you don't actually know it, and in fact, you don't really see anything different. So I think the way that they show that in the movie, and then he started running into all of this stuff which I didn't quite understand. I think the way they show that in the movie, I think it's not exactly how it would look, because my impression is when you're falling in, you would see an event horizon down below you, because the light, you still have light coming at you that's gravitationally lensed by this mass in the center, and so you would sort of see the black hole constantly below you, not have this kind of blackness all around you. So I didn't think that made a lot of sense in the movie. And then, I mean, as far as we know, you would just go straight to the singularity at the center. But however, having a singularity at the center of a black hole, or this mass distribution, is really kind of a hole in Einstein's theories, and understanding what's actually there probably involves some theory of quantum gravity, which we don't have yet, which we don't understand. So there could be lots of things going on in the black hole that we don't know about. But I think everything that was shown in the movie was probably science fiction.
And so one of the things that does happen in that black hole is that Cooper managed to communicate with his daughter using gravity. So let's ignore the black hole, let's ignore communicating back in time, but just in terms of communicating with gravity, is it possible?
Well, I mean, we have, gravitational waves. We've indirectly seen them from something called a Hulse-Taylor binary to pulsars orbiting each other. We have not seen them on the Earth. That's another really cool thing, since I'm always into the real science. We're looking for them on the Earth. Actually, Hardip is soon writing a blog post about this that people can read. It'll be partly on this. We are looking for them in Louisiana and Washington State and in Europe also for these gravitational waves. So gravitational waves are they do come to us from big supermassive black hole collisions and things like that, and we want to see them. So in theory, yes, you could communicate with them. Since we haven't been able to detect them, since their deviation over a 2-kilometer range would be about 100,000th the diameter of a proton. That's the kind of distance deviation we're looking for, which is very hard to see. it would be hard to communicate with them, but in theory, many things are possible.
I mean, from what I understand, they are essentially very, very weak, these gravitational waves. And the ones we hope to detect with these instruments coming up, LIGO, which I think goes live in about 2 years' time, and then there's space-based missions called LISA or ELISA. The only signals that we're going to be able to pick up, because of the fact they are so weak, are like the merger of two black holes or collisions between neutron stars. They have to be basically massive events that we could then just pick up. But I'm not quite sure I understood exactly what they were doing, trying to communicate with gravity and how that would actually be done from the center of the black hole. I just accepted the story and just switched my brain off at that point.
Fair enough, fair enough. All right, one last question about the black hole. And one of our viewers asks, if not even light can escape the clutches of a black hole's gravity, how could flesh and bone? How did Cooper escape? Is that possible in any possible way?
We have to assume that in the film, this higher advanced civilization, which was us in the future, if they could control and manipulate what he was seeing and doing inside the black hole and present him with all the views of Earth laid out in front of him, timeline for his daughter, then they had the capability to take him out and put him elsewhere. That's one possibility. Or also, if you go into a supermassive black hole on the right trajectory, supposedly, you can pass through and come out potentially somewhere else in the universe. So maybe he fell in the correct way to pass through the black hole and out again. But otherwise, it was this other civilization that put him where they wanted to put him.
I have to say, we really don't know what goes on in black holes. And as Eric mentioned, we haven't solved quantum gravity and singularities. Our physics always only goes up to a certain point. So the fact that there are black holes was a crazy idea from the last century, and we know they're there. We don't. So any question you're going to ask about what's happening inside, it's going to be hard to kind of answer and say one way or another. I mean, people have developed a lot of theories, but that's kind of where we are at.
Fair enough. So two final questions for you guys. And the first is, so personally, I thought Interstellar was a whole lot of fun. I really enjoyed the science concepts that at least were brought up to further the plot. And physicist Kip Thorne, who we've mentioned a few times on this broadcast, he was an executive producer on the film. And he has said that, he had the job of keeping movie makers from violating any known laws of physics. And his criterion for acceptance was, quote, something serious physicists would at least discuss over beer. Would you guys say that he succeeded in that?
Yeah, we actually have Bob Wagner at Stanford is a general relativist. He's done a lot of gravity theory in the past, and he wrote a series of 10 or 12 questions that he wanted us to go through and compute. So I think we're going to be posting that to a blog too. So yeah, there are a lot of things that, things like the time dilation that we haven't really seen in movies before, and the fact Kip actually did write all of this, and it was really great to hear from him. And he's publishing this book that I think we should point out is probably going to answer these questions, certainly for me, better than anything I could have answered. It's called, I think, The Physics of Interstellar, and he's writing papers on this. But there's a lot of physics in it. The whole graphics of the black hole, as people have talked about. And Eric mentioned lensing before. That's really not been seen, like how the light bends over. That's what lensing is. The light is being bent by the gravity back over, and so that's the most realistic depiction of a black hole that's ever been seen.
I think that Kip did keep them honest about the gravitational lensing, what you'd see around a black hole, the accretion disk, and stuff about time dilation, which is wonderful to see in a movie like that to do with general relativity. There, I think it was honest, and it lived up to the hype that it was accurate for that. But for many other things, throughout the film, it unfortunately had lots of holes in the science. So that bit was accurate. The rest, it was a story though.
Yeah, I didn't see any huge holes in the science. I mean, there were things that are taken sort of to a science fiction extreme, but I was actually very happy with the science, and I was excited to see something where the effects of general relativity are kind of put on the big screen. That's very
I mean,
cool.
you have to say there was lots of ifs. If a black hole could capture a planet, if there's such a thing as a stable orbit for a planet around a black hole, whether a planet could survive the tidal effect depending on what distance. There's a big if about the radiation environment in which it existed, etc. So there's a lot of ifs which leave the door open to saying, yeah, possibly these things could happen, but probably very extremely.
Great. So one last question for you before I let you go, and that is, if the three of you were science advisors on a science fiction movie, what concepts would you want to include?
Mandeep, sorry.
No, go ahead.
One I'd like to see is a neutron star, a pulsar. You can imagine maybe in a film when we're zipping around the galaxy in our interstellar spaceships, we're going to need some sort of navigational markers, otherwise we're going to get lost in the galaxy. And you can imagine a network of pulsars is one of those things that would give us a framework which we could use to navigate around. And a pulsar is basically a neutron star, or, a very dense stellar remnant. That's basically where the electrons and protons have been forced together. So you've got this very dense, compact object, which is rapidly spinning, and it's got an intense magnetic field. So you get these pulses. So, with an object spinning 1,000 times a second, you'll be seeing all these pulses at that rate. But these objects also flash in the visible. And what I'd love to see maybe is an interstellar pilot going past one of these basically interstellar lighthouses. And the fact that they're embedded in a supernova remnant would be a really nice backdrop. So, seeing all these interstellar lighthouses would be quite a cool thing.
Yeah, so I think actually this movie sort of, like I said, I'm excited to see general relativity kind of treated this way. I was excited to see a wormhole reproduced in a sort of realistic thing. I mean, it's this hyper dimension projected onto 3 dimensions. So you wouldn't see like a tornado sort of vortex that you see in a lot of movies, or Star Trek has this too, but you'd see something more like a sphere. So actually what he showed actually is what I would really like to see. On sort of another note, I'd actually like to see a kind of realistic treatment of exoplanets. Now that we're starting to discover a lot of these things, it would be interesting to see in a movie setting sort of just the range of planets that we've discovered, because I think it's more exciting than what Star Wars has shown. I mean, it's not like you have frozen planets and desert planets, but you've got hot Jupiters and you've got dwarf planets and things like that. So that would actually be really cool to see in a movie.
I think all those, I think for me, there's sort of the stuff that we know about in the universe, which is pretty amazing if you got up to it. Magnetars and pulsars and extreme black holes. But then there's sort of stuff that I really care to know about in the universe. I think we all care, like dark matter and dark energy. So what are these things that are very different and we don't know? Are we going to find dark matter? It would be kind of neat to see that portrayed in some way. Dark energy. Will the universe expand forever? Is there a multiverse? There's wormhole possibilities to other universes that I read about, whether or not they're real. But there's amazing amounts of stuff in the universe that we're always finding, right? Like all the time. And eventually it's all useful to us, but it would be neat to see things like that portrayed. There's the short-term stuff like gravitational waves that I talk about that I think we will see, but then there's the farther off stuff. And we humans are a good creative species, huh?
And hopefully we'll see all that on film sometime soon. That sounds great. Mandeep, Hardip, Eric, I'd like to thank you so much for joining us today. And thanks too to all the viewers who joined us and asked their questions. We got a lot of questions for this Hangout, and I wasn't able to ask all of them. So I will be sharing those with the 3 bloggers we have here, and maybe they'll be able to answer them on the Curious Stardust blog. If you'd like to see this webcast again, or if you want to share it with friends, it will be available almost immediately on both the Curious Stardust blog and on YouTube. And if you want to learn about future webcasts, please follow the Kavli Foundation and Curious Stardust on Twitter. Thanks again for watching.
Thank you, Kellen. Thanks everybody for tuning in.
Bye-bye.